So you'll notice that we have this set up as a series. The electrons will come out the end of the battery, go into the first 220 ohm resistor, come out of it, go into the second one, come out of it, go into the third one. So all three of these are 220 ohms. Then they come out of that, go into the ammeter, which remember that your ammeter has to be connected in the circuit in series for it to measure it, and then out the ammeter and back into the other side of the battery. Then whenever we go to measure the voltage, our voltmeter is coming out the end of the sensor, and we literally will connect it in parallel by just touching both sides of whatever it is that we want to measure the voltage for. So the first thing we're going to measure is voltage. I'm going to touch both sides of the battery to get what the voltage of my battery is. Now notice that it's negative. All that means is if I flip-flop my wires, then I'm going to get a positive value. So 3.19 is the voltage of my battery, 3.19. And I'm going to measure the voltage across each of the resistors now, again in parallel. I'm just touching both sides. So here's one resistor, 105. Here's the next resistor, 105. And I'm going to guess the last one will be the same thing, a little bit different, 107. Okay, so 105, 105, and 107, and that gives me the voltages in a series circuit. Okay, so now we want to measure the current. Remember that our ammeter needs to literally be in the circuit. So I have it connected straight to the battery. You can see that I'm getting a reading. It's oscillating between 509 and 458. So I'm going to go with 458 times 10 to the negative 3. Now I'm going to disconnect that. We'll move the sensor from the battery to the third one. So I'm going to move it and connect it into here by the third one. And notice that I have a 4.9. Again, it goes between the 509 and the 458. So I'm going to go with 458 to be consistent. Reconnect it. Connect to the second one. So connect that guy and that guy. Again, 509, 458. So I'm going to put the 458 down. And then I'm going to connect my last one here. And that's going to be there. And notice again, I get the 509, the 458. So I'm going to go with 458. And what that is on my sheet, I have the 458s, 458, 458. All of those are the same all the way around the circuit, which should make sense because shouldn't the same amount of electrons coming out of the battery here go through every single resistor all the way around? So now we want to look at these. So our resistances, remember R1 was 220. R2 was 220, and R3 is 220. And if I do V equals IR across the row here, then I end up getting a value for my total resistance of 683 as my total. So as I look at these down the row, I want to find what is the relationship of voltages when your objects or resistors are put in series. So if you notice I have this and this and this, wouldn't they roughly all add up to say that V1 plus V2 plus V3 gives me my total voltage? Then I can look at this and say, hey, don't those all look the same? So I can say that my total current is equal to my current across 1, which is equal to the current across 2, which is equal to the current across 3. And then I can look at my resistors here and say, hey, when I put resistors in series, I get a bigger resistance. And so notice again, that's going to be an adding up, a 1 plus 2 plus 3, and that gives us our relationship for the resistors. So now here we have a parallel circuit, and that is where the electrons have choices. So notice when I come out of the battery and come up to this side of the resistor, the electrons can either come through the resistor or they can go through the black wire up to the next one. Again, here they have the choice to come up through the red wire to come up to the next one. And then when they come back down on the other side of the branch, then notice that they connect back up again here, connect back up again here, and then go back into the battery there. So what we're going to do is do the exact same thing we did on the last one, where we'll measure all of the voltages, and then we'll go back and measure all of the currents. So when I look at trying to measure the voltage, the total voltage of the battery, I'm just going to touch both sides of the battery, and hey, guess what? It should come out to be very close to what it was last time. So 3.08, and that is going to be our total voltage, 3.08. Then I want the voltage across resistor 1, so I'm going to touch both sides. I'm putting this in parallel with that resistor. Notice that that is 2.9. It looks like it's bouncing around a lot there. I'm just going to go with 2.90, and then I'm going to check the next one. Touch both sides of this guy. 2.9 again. Just pick a number. Just going to go with 2.9. 2.9, and then this one is going to be also 2.9 something. Okay, so I have 2.9, 2.9, 2.9. And just to lastly double check again, the voltage across my batteries is going to be 3.0 something. Okay. Now, in the next part, remember that we want to measure current. So I'm going to have to literally disconnect a wire in order to make it happen. So to get my total current, I'm going to connect right straight to the battery. And notice that I get 3.9. Let's see if I connect those tight again. 3.97 times 10 to the negative 2. So 3.97 times 10 to the negative 2 is my total current. I'm going to disconnect, reconnect, so I'm going to take and pull, and now I'm going to pull these two off together. They have to connect to one of the wires, and then this has to connect to the resistor 1. And notice that that current is 1.3, just pick one, 8 times 10 to the negative 2. Then I'm going to connect and reconnect again, so I'm going to take and put this back on over here. Stick that there, pull these two off, and connect them both to this guy. And put the other side of the sensor into that one. And there, notice that we have 1.38 times 10 to the negative 2 again. 38 times 10 to the negative 2. I bet you can guess what the last one is going to be. Now, when you guess this, it's only because all of our resistors are the same, because all three of these resistors, remember, are 220. If they were different, then each of these would have different values of voltages and currents. And then I'm going to connect this very last one off and put the ammeter into that circuit so that it has to flow through the ammeter. And notice again that we get 1.38 times 10 to the negative 2. Okay, so again, we're going to fill in our resistor values. Remember that R1 is 220, R2 is 220, R3 is 220. You could take the voltage and divide it by the current, and you should get a number that is very similar or very close to that 220. We're just going with what the accepted values of the resistors were there. If I do that up here with my total resistance, I can take V divided by I, and I end up with a value of 77.6 ohms. So ohms and ohms and ohms and ohms. Just put that up here, and then this current is going to be in amps, and the voltage is going to be in volts. Now, again, if we look at relationships, so if I look at these, I could probably say, just real generally, that isn't the total voltage equal to each of the individual voltages? And when I look at this, notice that these add up. So I could say that my total current is I1 plus I2 plus I3. And then the last one, it's the resistor here. We get a really interesting relationship. So in a series circuit, remember that when we added these up, we got a bigger resistance. In a parallel circuit, we're adding these up and we're getting a smaller resistance. So what is the relationship whenever we add them together but we get something smaller? That's an inverse relationship. So we would say our 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. And if you calculate 1 over 220 plus 1 over 220 plus 1 over 220 and then flip it, the value you get is 73, which is really, really close to what we calculated based off of those two. Okay, so the last thing I want to show you is we're just going to extend this a little bit for fun into capacitors. So this top table is my table for series, this bottom table is my table for parallel, and I want to compare these relationships. So notice that in a parallel circuit, the voltages are constant but the series circuit, the voltages add up. But whenever you talk about currents, they flip-flop. A series current is constant or is equal, and a series current adds up. So notice how these two relationships flip-flop. Well, the same thing happens with our capacitors. In a parallel circuit, our capacitors are the 1/over relationship, but resistors are the 1/over relationship, but our capacitors, if we were to do capacitors, they are literally going to be where you add them up because it's the flip-flop of that series one. Then if I look at my capacitors in series, then it's going to mirror the resistors in parallel, and so it's going to be 1/CT equals 1/C1 plus 1/C2 plus 1/C3, etc. So now think through that. If I take my capacitors and I put them in series, 1 and 1 and 1 and here, then aren't I going to have a smaller amount of capacitance because of the way this is going? However, if I put them in parallel, which would be this guy, then I can take and think, well, I'm going to have a capacitor here, capacitor here, capacitor here, and they're all going to be hooked up kind of like this. So isn't that the same, if I put my battery here, as having like one big plate here, one big plate here, which is going to give me a bigger total capacitance? Okay, so now in summary of our lab, whenever we take and we put our circuit in series, the current is constant and the voltage adds up. So series current constant, series current constant. Whenever we have a parallel circuit, those relationships flip-flop where now our current adds up and our voltage is constant, so parallel voltage constant. So you often hear me say SCC PVC, SCC PVC, series current constant, parallel voltage constant, series current constant, parallel voltage constant. And if we look at the resistances, remember that in a series circuit, a series set of resistors is going to give us a bigger resistance, and in a parallel circuit, a parallel set of resistors is going to give us a smaller resistance, and we would use that to our advantage to determine to get the amount of resistance that we need. So a series, we get bigger resistances, and a parallel, we get smaller resistances. So SCC PVC and series resistors bigger, parallel resistors smaller.